More than that, we prioritize your safety and well-being to ensure everyone is familiar with the safety procedures and emergency protocols of this venue. We have arranged a safety induction from DoubleTree by Hilton Surabaya, presented in the following video.
Trained by Hilton Surabaya. These are the hotel emergency procedures. In the event of an emergency, the evacuation message and alarm will be heard, informing you to evacuate the building. Please follow the green fire exit signs and make your way to the lobby entrance. This is the emergency assembly area for the hotel. There is no maintenance or testing taking place today, so if any evacuation message is heard, please respond by evacuating the meeting room. If anyone requires medical attention, DoubleTree by Hilton Surabaya provide in-house clinic and has trained first aiders who will provide emergency medical assistance. Please inform one of our hotel staff for any assistance that you may require. The hotel emergency phone number is 5555. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. A very good morning. Welcome to the opening ceremony of the 4th International Conference on Multidisciplinary Application of Information Technology ICOMIT 2025. We would like to convey our very warm welcome to the Dean of Faculty of Computer Science Universitas Brawijaya, Dr. Triastoto Kurniawan, our excellent keynote speakers, Professor Romeo Marian from University of South Australia, Dr. Herman Tole from Universitas Brawijaya, Professor Yu Cheng Fan from National Taipei University of Technology Taiwan, the Chair of ICOMIT 2025, Dr. Bayu Priyambada, all distinguished guests and the participants. It is a truly honor that I welcome you today. My name is Ristika Kurnianestiorani as your MC today. We are gathered here not only to share knowledge, but also to build connections, inspire innovation, and create meaningful collaboration. We are delighted to have the participants joining us at this significant event where experts from around the globe converge to discuss and explore the theme of this year's conference, Crafting Smarter Solutions for Tomorrow's Industries.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Ladies and gentlemen, distinguished guests, keynote speakers, authors, and participants. First of all, I would like to express my highest respect to our deans, Hilkom Brawijaya, Engineer Triastoto Kurniawan, STLE, SDIPN, and also the vice deans of our faculty for their continued support. And also, I convey my sincere appreciation to Professor Wallace Mahmoudi as our former deans, and also our heads department for the presence and valuable contribution to this event. I truly an honor for me to welcome you all to the 4th International Conference on Multidisciplinary Application of Information Technology ICOMIT 2025 held here in Surabaya 25th and 26th August 2025. We are very pleased to have With us today, the scholars, researchers, practitioners, industry leaders who share the same passions in advancing the role of information technology in many aspects of life. The theme of this year's conference is Crafting Smarter Solutions for Tomorrow's Industries, to reflect our commitment to explore how cutting-edge IT applications can spark innovation to support sustainability and bring real impact to our society. We are fortunate to be inspired by our keynote speakers, Professor Melalui from University of South Australia, welcome to Indonesia, and then Dr. Engineer Herman Tuli from Philcom Brawijaya, thank you very much. And then Professor Yu Cheng Fan from National Taipei University of Technology, Taiwan, thank you. I believe their insight and experience will soon guide us in understanding the latest trend and future direction of IT. This year, we received about 88 submissions. After the rigorous review process, we got 64 papers that will be presented today. I sincerely thanks to committee and reviewers for their contributions. To all authors and participants, thank you for your contribution today. We hope ICOMIT 2025 will not only be pleased to present the research, but also as a platform to build collaborations, exchange ideas, and create meaningful innovations to face the challenge today and tomorrow. With that spirit, let us begin this conference together, learning, sharing smarter solutions for the future. Welcome to ICOMIT 2025. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, to formally open our conference, we are privileged to have with us the Dean of Faculty of Computer Science, Universitas Brawijaya, who will deliver the opening address. Please join me in welcoming Dr. Triastata Kurniawan.
Distinguished keynote speakers, Professor Romeo Marian from University of South Australia, Dr. Eng Herman Tuli from Universitas Brawijaya, Indonesia, Professor Yu Cheng Fan from National Taipei Institute of Technology, Taiwan, and our special guest, Professor Nubuo Funabiki from Okayama University, and Professor Chi Peng Fan from National Tung Sim University. Respected Vice Deans, Head of Department, Committee members, and faculty members from Faculty of Computer Science, Universitas Brawijaya, Indonesia, esteemed guests, colleagues, and participants, good morning. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera sekalian. On behalf of the Faculty of Computer Science, Universitas Brawijaya, welcome UB. It is my great pleasure to welcome you all to the 4th International Conference on Multidisciplinary Application of Information Technology, ICOMIT 2025, here in Surabaya on August 25th to 26th. We are honored to gather academics, researchers, graduate students, practitioners, as well as policymakers from around the world. ICOMIT has always been more than just a place to present research. It is a space for collaboration, networking, and exchanging ideas on how information technology can drive transformation across sectors such as education, manufacturing, agriculture, and healthcare. This system crafting smarter solutions for tomorrow's industries reflects our shared commitment to addressing global challenges and improving the quality of life. We are delighted to welcome participants from many countries and to host this event in Surabaya, a city of symbolizes the harmony of tradition and innovation. Selected papers will be published by signature and considered for inclusion in the Web of Science, ensuring international visibility for our contributors. I want to extend my deepest gratitude to the organizing committee, scientific reviewers, keynote speakers, and staff for their hard work and intense dedication. Without your efforts, this conference would not be possible, especially for the committee members. I know some issues were complex to address, and you all are already successfully handling them. Please let us give one applause to our committee members. Luar biasa, Pak Bayu and team. I am deeply proud of you. This conference will be both stimulating and inspiring, encouraging new collaboration and meaningful connection among us. I also invite you to experience the rich culture and warm hospitality that Surabaya has to offer. Once again, welcome to ICOMIT 2035. Thank you, and with the word Bismillahirrahmanirrahim, ICOMIT 2035 is officially open. Thank you. Assalamualaikum.
Dear honorable distinguished speakers, ladies and gentlemen, now I'm going to start the Q&A session. We will hear about the latest updates on information technology from the three speakers from the three different countries. Each keynote presentation will be followed by a Q&A session, allowing you to engage directly with your speakers on their topics. It's an honor to have our first keynote speaker from the University of South Australia, Professor Melalui. To moderate this session, we have Dr. Tirana Fatiamosa. Please join me, Dr. Tirana, to introduce our keynote speaker and facilitate the session.
Good morning, distinguished guests and colleagues. Welcome to ICOMIT 2025. My name is Tirana Fatiamosa, and I'll be your moderator for this session. Today, we have the distinct honor to hearing from a leading researcher in applied artificial intelligence. Please join me with a round of applause in welcoming Professor Romeo Marian to the stage. Okay, finally we have Professor Romeo Marian joining us. Welcome, Prof, to Surabaya. How are you today?
Thank you, everybody, and thank you for the organizing committee. Aren't we sitting outside a glorious morning to start this session, this conference? Thank you for having us here.
Thank you. And before Professor Marian presents his presentation, let me share a bit about his impressive background. So, Professor Marian is an associate professor of engineering at the University of South Australia, with over 30 years of experience in academia and industry. He is an expert in mechanical and mechatronics engineering and a leading researcher in applied artificial intelligence. With more than 160 publications, several patents, and over $7 million in research funding. Professor Romeo Marian has also held major leadership roles in engineering, education, and industry collaborations. Today, today's sessions will consist of presentations followed by Q&A sessions, and the entire session will last for 45 minutes. And now, without further ado, Professor Romeo Marian will present a presentation entitled Implementation of Industry 4, the Fusion of Physical, Digital, and Biological Worlds. Professor Romeo Marian, the floor is yours.
Thank you, everybody, for offering us the possibility to know you and to share our knowledge. I come from the University of South Australia, and we are at the moment merging with the University of Adelaide, and we will be from 1st of January 2026, we will be Adelaide University. So you will see my details, they will change, so my email will cease to exist at the end of the year, will change to Adelaide Uni. It's slightly different than the one I have now. What I would like to highlight is that this piece of work that we've done and I'm presenting today, I worked on it and I had my the help of my PhD student, Silver Jean. So he's a very good professional, and I work with also with Professor Jaban Chow, and there were a few people along the way who contributed significantly to the project, and they are Alexander Krotik, he's an engineer from Switzerland. We had Professor David Duncan Campbell, who was our head of school, and we also worked with Aled Ab, an academic at Baghdad University, and by my colleague Marcus Studio. Moving on, what I would like to highlight is what is the Industry 4, the fourth industrial revolution, but how it is different from anything else we see in manufacturing and we have seen for a long time. I will start by highlighting what the problems are, what the challenges are in trying to implement this system in academia and in general in industry. I say academia because we are in the first line of fire in something we have to demonstrate in industry that it's really worth moving forward. And I would then talk about what is the critical infrastructure if you want to get a system, generally we start in the lab. We will discuss about digital twins and how important they are and how they differ from anything we have in industry at the moment in academia. I will present you the system that we have built in UniSA. Took a while to get there, and on the system that we have, we implemented a few very interesting technologies. and one of them will be a novel control strategy for robotics. We will discuss about how to apply this concept of Industry 4 to produce resilient, flexible assembly. Assembly being one of the major parts in manufacturing that needs to be improved if you want to have a manufacturing system. And then we will go towards how we implement some aspects of artificial intelligence and highlight how this can be used for predictive maintenance. I will discuss a few aspects about the future trends in Industry 4 as we see it going through the process, and a roadmap to develop Industry 4 systems if you want to do it, and if you want to follow this road, probably it would be a good idea to get in touch with us because we are at the heart that we try to do this and make it match. I'll finish it in some remarks. So moving forward, you have probably you have seen Industry 4, Industry 4.0, the fourth industrial revolution, and if you are puzzled, that's a good way to start because trust to me, trust us to work in the same shoes some years ago. When you have, and the fact that you have some marketing people who try to get a bit of advantage there is not helping. But so Industry 4, or the fourth industrial revolution, is basically a new paradigm, a new philosophy of doing things in manufacturing and doing manufacturing better. But it started, so the term, the fourth industrial revolution, was coined in 2015-2016 by the World Economic Forum, by Klaus Schwab, who said there is something here that we can do to improve things. But a few years before that, the German government developed a manufacturing improvement system, and they called it Industry 4.0. That is, Industry 4.0 is about high technology and technology applied to industry, and Germany sells a lot of technologies, and it was only fitting to have a program in this area. Industry 4.0 is about technology, and I would like to highlight that on the figure on the right, we have technologies that for this ecosystem. However, the fourth industrial revolution is more than that. It's about, it's a new philosophy, is about the fusion of the physical, digital, and biological worlds. What do I mean by this? I don't want to make a mechanical project in there enough as they are, but I'm saying that you have the physical world, which is machines, equipment, things that cut metal, bend metal, or produce something. And then on that, we will have the whole control system is based on applications of IT, so information technology. You get the data, you collect it, you process it, and you go back and control the system. And when I say biological world, I'm referring to the part, so applied artificial intelligence. So what intelligent beings do, and the intelligent creatures do, we can look at them, we can look at the living world around us and see that there are many technical solutions that we could apply in our systems. But so the goal of this fourth industrial revolution is to create better manufacturing systems, produce better products, make them cheaper, make them faster. We have to have intelligent systems that produce products well and fast at a reasonable cost. I have the word there evolutionary. So everything in this area of the fourth industrial revolution basically is evolutionary. This is a good thing because you can start small and you can evolve. And as you evolve, you can improve and you can add other you can add algorithms, you can add other approaches. But the key technology of this Industry 4 is, would be the cyber physical system. So you have a system that produces the products that you make, right? And then they are connected, so they have sensing of the environment, and then you act on it. You have Internet of Things, so everything can be controlled from afar, or can be, so you can have algorithms implemented in external facilities. And then you have, on all this, you have the artificial intelligence that controls everything. Okay, so implementing Industry 4 is not straightforward, it's not very easy, but I think it can be done and it shall be done. So I would like to take you through the journey that led to the creation of an Industry 4 system in ESA. It starts with a philosophy, and the philosophy is implemented in a mindset. So you have the highest level of thinking there, so this will control the technology and control the national technology. But Industry 4 is so much more than technology. Is a philosophy of integrating the information you have. You can get synergies between different parts of the system. Right? And then you have a system that will co-evolve. Right? So we will get, so different parts of the system will move forward, will be evolved, and then as they evolve, they will break the constraints for other parts, which means you will have an evolution there. So why do we have to go to an Industry 4? Well, I guess everything we do can be done better. And we have the drama of two ladies coming to a party with the same outfit. So then is what if you would make every outfit unique, so that there is no possibility for that happen. So we have to go from the mass production, which was the second industrial revolution, to mass customization. Mass customization implying that you will not have additional costs or additional overheads in the production system. But we have to focus on flexibility and adaptability in Industry 4. And the core principles of this philosophy will be the interconnection of all the systems that you have, all the data in all the systems. You have information transparency. The information has to be available to the point where you make a decision. You have to consider decentralized decisions, so you have control systems of complex systems that each of them will work on a very small piece of from the local area, and you make a decision close to where it is applied. You have to consider technical assistance. Right? So if you have a system that has 2,000 pages of supporting documentation and something goes wrong, you don't have 3 months to go to the line of that booklet, but so you have to have a possibility for the system to determine what's wrong with it and where you should very fast have a few options that one of them will work. And you also have to consider cyber safety. You have to have control access to the system as it is now as today. So if you have a look at this list of principles, you have information transparency, you have cyber safety. How can you get them together? So is there a system in the world at the moment that has all this sorted out and basically working at the moment? And yes, they are. They are production life cycle management systems where all this information collection and information distribution is controlled and in control well. So being in tune with the present, where you have a lot of GPT generated images, I want to say to my favorite GPT, I say, okay, get me an Industry 4 image, and I got the image on the right there, when we have world, have the physical world, and have some information being shown there, and you have the DNA, whatever. I said, try to make it more industrial, and I've got the picture on the left here, which is again more industrial. So okay, put a bit more philosophy in that. This is where the GDP dies. So there are limits there. Okay, if you want to implement an Industry 4 system, and start with academia, because it's probably the easier way of doing this, what are the challenges? And the fundamental challenge that we discovered very early in our journey was the lack of physical product to manufacture. If you want a manufacturing system, you need to manufacture something. You cannot do an I/4 system on a computer, right? So you can't do that. Then if you have some machines or some robots that you can use to produce such a system, well, they will need to produce something. And we have to think of producing something that will not lead to a lot of waste, because the administrators would be unhappy with us, right? So that was probably the first hurdle. And once we cleared that, we realized there is a way forward for this case. So another challenge is technological. We need multidisciplinary expertise for anything we have, and we need a significant infrastructure. So you have to put things together, but everything that you put together, every part of the system has to have an expert around. And it's not easy to have expertise in everything. But well, this is one of the major hurdles why you don't see these systems widespread. Security, cybersecurity, you have to protect the system, you have to make sure you don't have unauthorized access. And also we have one extra layer of complexity, which is academic specific, right? Which means you have processes that need to be followed in academia, and especially you have administrative processes, and they tend to follow rather than need the new technologies. And sometimes they lack that by a large amount. Right? Okay, so if you were to implement such a I/4 lab, which we did, you have to start by determining what you will produce. You will have to have some sort of physical components, and they might be flexible manufacturing systems. You might have modular stations. You might have CNC machines. You might have robots or robots, 3D printers. You choose what you, I mean, basically, based on what you have and what you can get your hands on, you probably can adapt the system. IT-wise, you will need a robust network, right? And you will have to have the bandwidth to control the systems, right? And when it comes to software, we were very fortunate at that time to have access to two PLM platforms. One was the 3D Experience by Dassault, and was one the PLM from Siemens. You had it, and it's okay, that's used. You need also manufacturing execution systems, and you need enterprise resource planning tools. Right? So if you have them, or if you don't have them, what you can do instead. Right? Very important for Industry 4, we have digital twins. And when I say digital twins, many Spanish people say, well, we had this for the last 40 years, we have not as well. Digital twins not 10 more. Digital twins are often more, and it, if you figure it correctly, you can have real-time monitoring of the system, control of the system. You can do simulation, you can do optimization, and you can do evolution. So it's the digital twin is different layers of information that you have about the system and how the system evolves. It's critical for Industry 4 and facilitates very important bidirectional data transmission. So at minimum, you have a system that will collect data and will process it, but then will send back data to the cell. So whatever you have in your manufacturing system, so you have a bidirectional transmission. Okay, so how do we implement this in our system? We combine physics-based and data-driven models, and we brought high fidelity of the system. So we started by CAD models, by geometric modeling. We had the visual representation of the system that we have built, and then you have physics-based model. You have a CAD system. Then you can add masses, distribution of masses, you can add inertia, you can add constraints. Right? So normally in a computer model, if you have two robots, they can come and intersect each other, there's no problem. Unless you switch, you have a switch that say, no, you cannot. Once you touch, basically you cannot go that. So we have the geometric modeling, we have the physics-based modeling. And this was was implemented in MATLAB, and we bought the app from there. And then you have data-driven modeling, where you can develop intelligent algorithms for prediction and anomaly detection. So you have a lot of IT embedded in the system from scratch. Okay, so I would like to show you how we did this in USA. So we had two cohorts which were gathering dust at that stage, and I had my student from Switzerland came for a short internship, 3 months, and also doing his master thesis. I said, okay, can you help us with this project? He said yes. Was very good, very knowledgeable, and basically he started, so in order to put almost together, we set our eyes on a set of product, and we started building the digital twin, I mean the CAD model and then the digital twin. We used for the system, we used Siemens NX, so this was from Siemens PLM ecosystem, but it's a CAD modeling, and then we used NX mechatronics, which permitted the control of the whole thing. And we used MATLAB simulating for the physics-based and data-driven models. For the middleware, so all the connection was done through OPC way, and if you have a look at the robots, one is orange and one is blue, so two different vendors, and one was open source and one is proprietary information. So might say, okay, we don't have the same robot, yes, but the fact that we have two types of robots that allow us to develop specialist, so demonstrate this as a feature, right? And we have, so the physical system is an extension of my PhD in assembly optimization. So I wrote a paper in 2003 saying, what if you have a flexible system that will adapt based on the product you make? And the product you make might change, and I have, probably everybody has one. You have a mobile phone, so each vendor of a mobile phone will have a number of models that they sell in parallel, and every model will be pretty much changed at the end of the year. So if you have a robotic system that will assemble mobile phones, what if you get the set of the kit parts of a phone, and the kit parts, when you get into the assembly cell, they will trigger a specialist, assembly sequence, and then the robot will start working on that one, will assemble it, will send it out, and then another one comes, and that might be a different phone. You don't have to stop, retool the whole system, assembly system, and then get it to a new model. No, you can do a change on the fly. But we have, this concept was designed to have a variety of products, and that can be changed with minimal intervention. the goal of this approach was to demonstrate that we can do exercise of one. So we can do products that will be absolutely unique and can be changed without overhead. We developed a control strategy for this task allocation and moving ahead. Right? So when I came with this idea in 2003, we had industrial robots. Industrial robot basically, it's a robot that is covered, which has all the programming and all the related development. But it's difficult to access every axis. At that time I said, okay, give me a robot, cut the cable to the cable and give me the possibility to get the control. Just happened that robots can do that. And the robot basically can access every axis. Well, can use it as a system in itself. And so the control strategy that we developed was, instead of going with a program for the product, we split that to individual operations. So an operation is the quantum, so the atomic element that we can solve. And we could, so we eliminated the need for reprogramming, and using OPC way, basically everything was controlled. Instead of the control system of the robot was controlled by the specialized. And here is the product that we use. So we needed something that is cheap, that's easy to make, but reasonably fast to make, and can be assembled in a variety of ways. So we have the Tetris like puzzle, and you can have, I'm not saying an unlimited number of options, but it's a very much number. I mean, if you have to look at how many ways you can get together a Tetris puzzle, it's a very large number. And so we have we came with this idea, and once we had this product, we knew that it is possible to do this project. We implemented the control strategy in the assembly cell 3SA. We have two cohorts, a different vendor, controlled by a central unit. We demonstrated the possibility to assemble different products without reprogramming. So basically, each product was split in individual notions that you need. Basically, you control, get a part, right, and place it somewhere based on that configuration of the product. We managed to achieve batch size of one production model without any overhead. So this was one of the major things that we did. We managed to demonstrate this. Okay. Then another research that we did was building resilience. What happens if things don't go according to plan? So things go, so things break down, things don't go well, and what do you do in that case? And if you have a complex system, the more complex the system is, the easiest is for something, the higher the volume for something to go wrong. So we try to build resilience to this, and at least would be the capacity to withstand disruptions. If a disruption occurs, how to recover and how to resume a function, and very key feature, if a robot goes down, the two robot cells can still work at half the capacity without having to stop it. So the idea was we have to reprogram on the fly the whole thing. Right? So if the robot goes down, it stops, it can be removed. Right? The new robot or the fixed robot can be brought back without the cell stopping. If you have a full robot cell, if you are careful in how to program it, you can get it to work at about 75% capacity. And we have to determine, so we have the resilience in build so that the system will work without stopping if a robot will fail, or if you have this in a flexible production system, one of the machine falls down, and okay, you can fix it. You have to do this without the need to reconfigure the whole process and without the need to reprogram if you add a program memory. So it's very important. I give the example of the mobile phone. If one of the phones will get out of style, you take it out, you program a new one, and you add it to the mix, and when the new, that particular type of phone will come, you can system on the fly without any added overheads. But so we implement the new strategy in the sense that each robot was the backup for the other robot, and we did a number of experiments. So if the robot is not viable, is taken out, the tasks allocated to that robot will change to the valid robot, and we did experiment with just stopping the robot, with hitting the red button, and the whole thing kept going, and demonstrated with a couple of different scenarios, that we can achieve this dream of raising the reputation of capabilities without having the system in the blue line was minimal disruption in the whole seconds. If you have a robot that's in standby and one of the robot stage, and you take it out, push the new one in, and then restart it. Or if you have so you have another strategy, the type 1, which is better, and that will be a manual restart if something goes wrong. Okay, benefits of this strategy would be that it's cost effective. You go in, you have duplicate robots, duplicate components. You can duplicate if you want, if you have a few robots, you can have a spare one. If you have 6 robots in a cell, you can have a spare one that will be pushed in if needed. If you have to keep the production, otherwise the production level will go to about 1 less. So it's an efficient system. You have automatic switching to a backup robot, and the whole system will have higher resilience to trace implementation capability. Right? Okay, we also tested the application of AI in the system, and we selected the predictive maintenance. I will just highlight that we got the whole thing sorted out, and this is at the moment waiting for to be presented at the conference. There is an embargo there, so I will not talk a lot about this at this stage. It's just that I will invite you to send papers after they are published in December. The idea is that we will collect the data, we collect the temperatures, we collect the details of the system, and work on them. And we use operational data encoder, auto encoder for movement detection. We got all results, and they are being there over the satellite. Okay. Now, future topics in Industry 4 as we see it now. You have bidirectional digital twins, you have evolutionary systems. You can start somewhere and then evolve. So what I would tell you in closing, getting close to the end of this presentation, you don't have to start with all sorts. You can have 4 wheel cards on which you add capabilities as you go along. But technology evolves, technology becomes available, and becomes available at reasonable prices, and you can add these layers on the system as you go forward. Bidirectional digital twin is the critical ingredient that will permit the evolution of the system. Right? And so the AI-powered predictive maintenance is very important, very powerful. I mean, you name a system, a critical system. If you have something like this, it's a dream of maintenance. They will, if you have something like this, basically you will have a technology that is needed by everybody. And moving forward, there will be higher integration between humans and robots. But robots are very good because they can work with humans next to them. If they get the job, they will not kill the person, but they will stop in time before doing that. But when it comes to academia, it's very important to have it in the mix. Academia is the place where you can test new ideas, you can try to see if they work, and try to do this without the danger of having to have a production plan at the end of the month. But you can develop everything there. So if you can do it, by all means, this is an area where you probably should spend a little bit of effort. But you can make a lot of contributions to education, research, and industry. And you can get hands-on experience with it. And when it comes to developing this facilities, you have to start by convincing your team and your head of school deans and vice chancellors so while endeavor. But to start with a pilot deployment, a simple thing that works, and on that one you add different systems as you can, as time permits. You do curriculum integration, you integrate what you do in your curriculum if possible, and you will have a lot of projects if you play your plans right. You can evolve the system, and then you can be a place where people in the region will come and discuss all of that, and where you can demonstrate that. So, just to finish, Industry 4 is transformative and it will shape manufacturing. It's not an evolution, it's a revolution. It's well beyond what individual technologies can do. But digital twins, you have predictive maintenance, will be key enabling technologies for doing this. You can develop resilient and adaptive systems, and this can be equal to the industry. ICOMIT is the backbone of everything. So if you do the science or information technology, you are in the right place, you are optimistic. And academia has a vital role to play into driving this evolution. And just a question to finish: how do you make sure that you are immune to GPTs and LLMs? Right? And how will this if you have this can give me an answer to that they are somewhere.
Ladies and gentlemen, moving on, we are excited to introduce our second keynote speaker from Universitas Brawijaya, Dr. Herman Tolle. I will hand over this session to the moderator, Ms. Intan Sartika, to introduce our keynote speaker and facilitate the session.
Good morning, distinguished guests and colleagues. It's my pleasure to welcome you to this conference, and I hope you have been enjoying ICOMIT 2025. My name is Intan Sartika, and I will be moderating the second keynote session. It's an honor to introduce our distinguished speaker, Dr. Herman Tolle, who will share his insight and expertise on how natural user interface are shaping the future of immersive digital experience. His extensive work in this field provides valuable perspective for both researchers and practitioners. Without further ado, please join me in welcoming Dr. Herman Tolle. Please give a round of applause. Good morning, Dr. Herman. How are you today?
Good morning, Vitan.
Thank you very much for joining us. And before Dr. Herman presents his topic, let me share briefly about his profile. And he is currently served as the Vice Dean for Academic Affairs at the Faculty of Computer Science, Universitas Brawijaya. He earned his doctorate in Information Science from Sakai University, Japan, his master in Electrical Engineering from Bandung Institute of Technology, and his expertise spans from information retrieval, augmented and virtual reality, mobile application development, and human-computer interaction. Dr. Herman has received numerous awards, including the Best Paper Award at ICOMIT and the Outstanding Lecturer Award from Universitas Brawijaya, and has shared his work at conferences in the United States, Singapore, and Indonesia. Today's session will consist of a presentation followed by question and answer session. The entire session will last for 45 minutes. And now, without further ado, Dr. Herman will present a presentation entitled Nature User Interface for Digital Immersive Technology. Dr. Herman, the floor is yours.
Okay, good morning, everyone.
Morning.
Yeah, first of all, I would like to say thank you for Phil community to give me the opportunity to as the keynote speaker today. So, yeah, today I will talk about the natural user interface in immersive digital application, enhancing usability, immersion, and presence for augmented and virtual reality application. So this is a part of our research work in MTA lab, Media, Game and Mobile Technology in Bilbao, UP. So this is the outline I will talk today about the why most immersive technology fail, about the digital immersive technology, natural user interface, accessibility, pyramid, and method to improve usability, presence, and immersivity, and I will show you some of our research work and results. So, yeah, I will start with this question: why do most immersive applications fail to be used despite their advanced technology? As you know, one of the one breakthrough technology by Google is the Google Glass, but it failed to be adopted by the market. So why it's failing, we will see some reason. But before I will explain what is digital immersive technology, maybe some topic related to Professor from here before presenting. So immersive technology refers to technology like virtual reality, augmented reality, and mixed reality that create realistic, interactive 3D experiences by blending digital content with the real world. So this technology aims to engage user sense to simulate presence in a digital or enhanced environment, enabling users to view and interact with simulated object and environment. There are some new technology. Not really new, but there are some previous technology, but part of the immersive technology, and there are also as well as new technology like augmented reality, virtual reality, mixed reality, as we call it like XR or extended reality, and digital twin, haptic technology, even AI and machine learning is a part of this immersive technology. And other one is about the metaverse. So this is kind of immersive technology we talk about. So I maybe just talk about two most popular immersive technology like AR and VR. I will explain briefly about what is AR and VR. The VR means that all we see, all we interact is generated by computer. So when we in the new environment or new area, that we feel that we in the different area with what we exist and all generated by computer. This is a virtual reality. It has some characteristic like 3D stereoscopic display. It means that we can see some realistic in our front of our eye when we use like VR box devices. It has a wide field of view display, wide field of view, and it has low latency and tracking. So it means that when we move our head, then the visualization of what we see, what we saw is based on the movement of our hand. Then we feel that we are inside or we are here in that visualization in the area. And the difference with augmented reality is we have the real situation, and then something generated by computer appear through, for example, using our mobile devices or other visual display. So it's called augmented reality. The characteristic of AR is it combines real and virtual, it's interactive in real time, and it's registered in 3D. So when we, for example, we have some marker, we call marker or code, and we use our mobile devices, and we see through our device, then we can see some object appear through our devices, interactive and registers in 3 dimensions. So the use of image technology in a lot of area, almost every area in our life. So it's for example, in games, in shopping experiences, in tourism and navigation, for entertainment, for education, for marketing, for retail, as well as for the gaming industry. So the usage of the AR and VR is very wide right now, as well as in the medical and healthcare implementation of VR and AR. So why this technology failed? I show you some of the failed technology, like Google Glass, like the Magic Leap one. If you ever heard about that technology, maybe we ever heard about Google Glass, the hype at maybe 5 or 10 years ago, but there's no product right now. And Oculus Rift, the first version, and as well as the Google Cube Plus, we can use controller for painting something. Most of the problem in that technology, I just bought it. For example, not intuitive experience, not seamless, not friendly for casual user, and too complex for average user. So that's the sum of the point that make the product fail. But in the other hand, we have some other product that succeeds. For example, we have a Pokemon Go. If you ever play the game, it's an AR game, as well as Beat Saber virtual reality games. We can play sword with music rhythm, and as well as the Google Expedition and other sample service IKEA Place, Nintendo Wii, and Nintendo Switch. Most of this application has strengths in usability and natural user interface. So it has an intuitive and accessible. It has high social engagement. It has natural control, easy to learn to use the application, easy to use, and it's wide access to the content. Other thing is they have intuitive control, how to use, how to play the game, and it has natural interaction, and it has strong social and family engagement, and it has the controller that we can use to control the application just using our natural gesture. For example, I can play volleyball using Nintendo Switch. I can play volleyball in real situation. I can play table tennis like in the real situation using my hand to play table tennis through this kind of technology. So we use our natural interaction. So that's why the technology has success in the market. So I will try to highlight what caused some product fail and what the parameter make the product successful. This is just a simplification to some of interesting point. The failed products has low usability, has unnatural interaction and irrelevant content. On the other hand, the successful product has a high usability. They optimize the intuitiveness They have natural interaction, accessibility, and contextual relevance. So that's to make the important point to make the some product get successful in the market. So this is the UX pyramid. Actually, it proposed by Stephen Anderson, 2011, about the user experience hierarchy of need. And I think it's relevant right now. When we develop any kind of application, any kind of software, including without emerging technology, all application, all software should have the first base to complete is the functional. Every software has the functional working well. If the functional is not working, it does not finish software. So functional is the base of any kind of software. But a good software or good or any application with all functional working is not a good software yet until it has the next layer. We call it reliability. For example, if many users connect, system not down, it's kind of a reliable thing. And good software with good functionality, with good reliable, is not a good software yet. It should be as a usable. Usable means it's easy to use. It's people can learn through the application without no need to get some tutorial or some help from other people. They can use by themselves. They can learn through the application. That's the usability. And the next level is about the convenient, pleasure, and meaningful. So if we want to develop a good software in any kind of software, we have to consider about this pyramid. So in our lab, in our research, we are focused on how to make the great software, make a good software within the focus on the third layer up. So through the usable, convenient, pleasurable, and meaningful variable. Because the functional and reliable it should be every software should be fulfill the functionality working well. This is the separation. So the third three part based on objective, qualitative. For example, we measure how the system working. We use like a black box testing, etc., to make sure that functional is working. But in the upper third layer is about subjective, qualitative. So most we ask to the user how they feel when they use the application. So even our function is working, but if the user feel difficult to use the application, so that's not a good application. So that's the point. So why usability is important in here. So I will talk about the natural user interface. We have some history from CLI to NUI, command line instruction. So natural user interface is an interface that allows users to interact with the technology using natural human behavior. Like we use our daily gesture, we use voice command, we use eye tracking, motion sensor, etc. So the goal is make technology feel invisible by enabling seamless human-like communication with system. So we can communicate to system, to computer, using our daily activities, daily gesture, with easily. So the history of the natural interface based from before we learn about the computer programming, or we give the how computer do our program through command line instruction, and then we move to graphical user interface. Until now, we still use the graphical user interface in our computer with Windows, and then even in our mobile phone, we use touchscreen. It's just still graphical interface, but it's a part of natural interface when we can interact through the new gesture. So this is a natural interface mostly used in any application right now. We can use to communicate through the voice command, hand gesture, even body gesture, etc. So the goals of natural user interface is intuitive interaction, leverage human natural abilities, seamless integration, accessibility and inclusivity, and then immersive and engaging experience. So provide a sense of presence and realism, especially in virtual reality, efficiency and productivity, context awareness. Yeah, that's the goals of NUI. Maybe I will make it quick. So one of the goals of the interaction is about the presence. Presence is a psychological state in which even though part or all of an individual current experience is generated by technology. So the feel of being in other place while we are not there. So that's the presence. So that's the goals. So in the natural user interface, there are two main goals. First is immersion and presence. Immersion means the extent to which technology delivers a vivid illusion or reality to the senses of a human participant. When we feel like we are doing something normal, it's immersive. Doing something like everyday activities, doing something that we feel like everyday activities. And then it will contribute to presence, a state of consciousness, the sense of being in the virtual environment. So if we develop a virtual reality, we want to make the user feel that they are in other place as they see in the display. So we call it as a presence. So the goal of VR is to create a high degree of presence that make people believe they are really in a virtual environment. So the goals. So when we through the VR and we feel that we are in other place, that's the application is working with. There are three types of presence: personal presence, social presence, when we feel the other people's way, and environment presence, when we can interact with the system. The personal presence, when we feel that we are inside some area. Social presence, we can interact with others. And environmental presence, when we can interact with the system. Yeah, the goal of VR is to create a heightened sense of presence. Oh, people say, tell us less. So the last sentence say, people who, for example, people who are afraid of height will also be afraid when using VR that the big the head. This is just some sample of the application. It's not making by us, but I got the video from you. So when we use the VR devices, then we feel like we going to the elevator, to the upstairs of the building, and when the upstairs open, elevator open, we have to walk through the that's what we see, and that's what the user see in the devices. That's what the user see through their eyes. So they feel that they're in the top of the building, in that space. So when you feel the
oh my god, oh my god.
Space, then you will feel that space. Okay, so that is the example. This says that we feel that we in that place. So we develop a new method for, we call it XDLC, XR Development Life Cycle. We modify some part. We call it Integrated Immersive Usability Model because based on my experience before, we have some important point in our design of the application is about the usability, immersion, and presence. So when we want to design some application, especially in digital immersion application, we have to consider about these three keywords. So this is the model, we have like 6 steps. First, we identify user needs and context, and then we ensure usability principle. So usability is not just measured in the end of the software development part, but it should be designed in the beginning. So we have to decide how to make people easy to use our application, how to make people can intuitively use our application. We have to design it, not just measure it. So then we reduce cognitive load. We have to reduce cognitive load. Cognitive load means that something user have to think, something user have to remember. When they use our application, they should not to remember something. What the function of this button? What should I do next? People should not to remember this. They just see everything and they know how to use, how to interact with the system. That's the cognitive load. And we have to enhance the immersion and strengthen the presence. What we should do to put in our application, and then we evaluate and iterate. We make some model like this. For every step, there are some goals and what to do and what the output. This is the method we develop in the lab, and we try to implement it in some application. So now, technique to generate strong presence is to use multiple dimensions of presence. Like we create rich multisensory experiences. So when we interact with system, not only by control something to click something to interact, but we can use our hand, we can use voice command, we can hear something, we can feel something, we can touch something. So many sensors. More sensor, more interactive, it can make we can make presence more better. And as well as social interactions, people or users should be feel he or she is inside the system. There are interaction with other something inside the system, and environment that is to the user. That's the point to create a strong presence. This is the how we design strategy for strong usability, high immersion, and strong presence. So what we should do? It's better if we can implement all, but it's not easy to implement all. But this is the other part about the development and coding thing. So you have to make sure that you can develop the software. You can make the implement the coding. But this is how we improve the usability. This is a sample of how we use the more sensory to interact with the system. We can feel like we can fly like a bird. This is not do by.
Can dive.
Okay.
Soar.
Soar, sure.
If you wanna push them in the opposite direction. If you want to gain speed.
Okay. It's kind of hard.
Up to here.
I was flapping my arms to fly through New York, and I saw a lot of buildings and cars below, but the cars were not moving. And if I looked way out to the side, I could see my little wingtips.
Okay, that's comfortable, kind of.
So not just what.
It's very sensitive to how you're moving your hands to control the wing tips. If you stop flapping, you kind of slow really abruptly, and then if you turn, you kind of veer around
We
and
feel
swoop
the
up and down.
sun in front of us, and we have to move our hand to fly higher. This is what the user see. So this is the sample of how we integrate many sensors to make the people feel that she or he is dissociation of flying. This is what people, the users see. They can move to the left or to the right.
It was less like actually flying than I kind of expected it to be, and a little more queasy making.
Just kidding. Okay, so other thing we can use usability heuristic and human factor psychology and design principle. This is almost same thing, but proposed by different people, and we try to combine it. We have a 10 usability heuristic. There are 10 points. For example, about the I mostly like number 6, recognition rather than recall, for example. So when we interact with application, it's better to make user recognition something rather than recall, to remember something. What the function of this button? What I should do next? People can understand directly to the application, no need to learn it before. So that's the good application. So there's some method design that we can use to implement our application. And this is some modification for the pyramid. We just make it in 4 levels. The first level is functional and reliability. The second layer is for usable. And the third layer for pleasurable includes immersion. And the last meaningful includes presence. What we should measure. But before it, what we should design, and then we measure. If there are some measurable parameter and there are some instrument to measure it. Okay, this is some of our research work in our lab. There are some research contributors, so it's not all by myself, but by my students in the field of UB, especially at MG. So there are some aim of the research. We try to increase the usability, the immersion and presence of the immersive experience application through the implementation of design principle. So we try to implement design principle to how to increase the usability, immersion and presence. And we design and implement new gesture. If there's no gesture yet, we design new gesture for natural interaction with the high usability, immersion and presence for specific purpose on education, cultural heritage and tourism in some specific areas. But the final goal is to provide a major framework for developing immersive application with high impact. That's the main goal. There are 2 reasons. I just show the VR and AR application. For the VR application, we implementation of natural hand gesture on some application, and we try to enhance new gesture as for specific uses and control function, and we enhance voice command for interaction, as well as for AR application, we improve the usability and immersivity on AR application with more engagement in interaction. Yeah, this is one of our research work, but actually I will not explain about this vehicle metaverse. But anyone, if you want to play, you can just get the QR code, and you can try to. You can join our metaverse vehicle. You can feel the building of vehicle. It's kind of metaverse. So when you join, and many people join, you can meet each other there. So we call it like a metaverse, and that is social presence. So we can meet other people there, we can talk about it. Actually, it's a kind of metaverse. We just develop. You can try if you want to try. You can interact with others. You can create your profile there. Okay. First, we use hand gesture control on virtual reality. We use like a device like Oculus Quest. It has the new one, Meta Quest. It bought by Facebook. Oculus bought by Facebook, and they changed the name to Meta Quest. Meta Quest 2, and they have new one is Meta Quest 3. So we use a Meta Quest 2. It has a 4 camera in front of the devices. Through the camera, it can capture our hand, for example. It can capture area, and then system can try to understand, recognize the hand gesture. So this is a kind of technique for recognize the hand gesture. But in this existing system, in MetaQuest, they just has this kind of basic hand gesture for point and pins, for pins and drag something, and for touch something. And then in new one, we can make an air tap, and we can swipe something. So this is just a basic hand gesture inside of these devices. And then we try to use this for multimedia player with hand gesture. As you can see in the video, this is a capture from user when he use the hand to swipe the screen. All virtual. Swipe left, swipe right, and then push the button for play the movie, for example, or change to other movie. They're still working for. And then, for example, for playing a movie, and then there are some button for play, stop, etc. Okay, let's continue. We have to evaluate the immersion. We have the immersion evaluation compared to using the controller and using the hand control. So we can conclude that using hand gesture is more immersive compared to using controller. And we also have the evaluate the presence. It also shows that using hand gesture is more presence than compared to using controller. This is just a comparison. And other thing we made is a traditional game with hand gesture control. This is also made by our student. It just illustrates how to use it. So this is the game about learning about the traditional cake in Banjar in Kalimantan. It's kind of.
Ini adalah wadai kalalapun. Ciri khas wadai kalalapun adalah warnanya yang hijau dengan parutan kelapa di bagian luar dan gula merah cair di bagian dalam. Wadai ini terbuat dari tepung ketan, gula merah, daun puda, air kapur, dan parutan kelapa. Untuk membuat wadai kalalapun, kita perlu mencampurkan semua bahan tersebut hingga menjadi adonan. Ambil adonan secukupnya dan giling menggunakan tangan sehingga berbentuk bulat seukuran buah langsat. Tambahkan potongan gula merah pada bagian dalam adonan. Setelah semua adonan selesai digiling, rebuslah hingga masak. Angkat wadai dan taburi parutan kelapa agar tidak melekat satu sama lain. Saya pesan wadai yang berbentuk bulat dengan lubang seperti cincin dan berwarna merah kecoklatan.
And then we as a player we can choose which one, we take it and we give to the.
Ini benar wadai cincin yang saya minta. Terima kasih. Ini uangnya.
Saya pesan wadai yang berbentuk bulat dengan lubang seperti cincin dan berwarna merah kecoklatan. Ini benar wadai cincin yang saya minta. Terima kasih. Ini uangnya.
Saya pesan wadai yang berbentuk seperti bunga dengan 6 kelopak dan berwarna kuning kecoklatan. Ini benar wadai bingkai yang saya minta. Terima kasih. Ini uangnya.
Okay, yeah, just skip. Yeah, it has a good physics and as well as control naturalness and low cyber sickness score. So in VR we have a cyber sickness issue as well. And the other one is VR for disaster mitigation, education.
Baik, saya akan melakukan demo atau testing dari aplikasi saya, MBC Setup. Saya bisa lihat scroll button.
How to control the system.
Berjalan.
So this is the view of the user. We capture the view of the user.
Hook. Transformasi.
So first, before they use the game or use the system, they can just try to using their hand gesture to interact with the system, so they know how to interact, how to push the button, how to use.
Lalu selanjutnya album video transisi. Ada 5 button.
Okay. Yeah. Other one is about tourism and cultural perspectives. Yeah, this is how we try to it's a kind of tourism application. How people want to explore, for example, the Malang city through this VR application. The first thing is try to understand how to control, how to take something, push some other button for information.
Cagar budaya merupakan kekayaan budaya bangsa sebagai wujud pemikiran dan perilaku kehidupan manusia yang penting artinya bagi pemahaman dan pengembangan sejarah, ilmu pengetahuan, dan kebudayaan.
Yeah, and then, for example, we want to explore Malang City. For example, we have the map, and we have to click to some other place, and then we can go to that place. So in the area of VR, we call it the teleporting, and then directly we are already in some other area. For example, yeah, we're in
Gereja Katedral Malang adalah salah satu rumah ibadah untuk umat Kristen. Bangunannya yang unik menjadikan gereja katedral menjadi salah satu rumah ibadah terindah di Indonesia karena mempunyai gaya Eropa.
Okay, and other one is about the virtual practical for electrical engineering, because for this practical we cannot just use the base control in the application. We have to create a new gesture. We have to how to handle an object, how to turn on the switch, how to final switch in practical, because so we cannot play. Yeah. Yeah, the first part of the application, they have to teach the user first. What is the important part? How user can, how they can try to get something. They can use some information. Yeah, and then we start the introduction about the practical. There's some video, and then the circuit.
Halo teman-teman, perkenalkan nama saya Dimas. Saya Benda. Jadi, selamat datang di experience pembelajaran listrik dinamis menggunakan virtual. Untuk menggunakan hukum Ohm. Hukum Ohm menyatakan bahwa kegiatan listrik sebesar V pada suatu medium listrik dengan hambatan R adalah sama dengan arus listrik I yang melewati medium tersebut dikalikan dengan hambatan R. Jadi, untuk mencari hambatan lampu yang ada di papan percobaan di depan, kita bisa menggunakan rumus T sama dengan I dikali R strik. Kita bisa melihat informasi yang tepat.
And the other one in AR, we try to develop AR application with Avatar as a partner in learning, with multisensory visual, with sound, voice, and touch. And this is what we designed for the system. So, for example, user problem is the user feel confused about how to interact with the application. So we use an avatar to interact with the user, for example. So this is the video of the application, the AR application. There are some, we call it avatar, as a friend of user to learn something. So using this avatar.
Wow, lihat, ada satu ekor anjing sedang bermain di taman. Yang lucu ya, ayo kita hitung bersama-sama.
Because mostly AR application
kamu anak hebat.
Someone to help them to use, not give the instruction how to use.
Ini angka 13. Punya 13 ekor. Ada ayam jantan, ayam juga tumbuh bersama-sama. 10. Kamu anak hebat. Ayo belajar lagi.
So we try to evaluate this application to some of the schools in Malang City, especially not in the general school, but as well as for the autistic student. So this kind of AR application is not working good for normal student, normal kids, but also working well for the autism student when they usually has distraction on learning, they has difficulty on learning something. So this application is so the good result. Okay, so the disability key to success, because without disability technology feels complicated and users are frustrated. That's the point. So yeah, so this is the conclusion for our presentation. That we have developed our method, and we hope that method can be used to improve the usability, the immersion, and the presence of the immersion application. I think that's all from.
So, ladies and gentlemen, for the final keynote session, we are privileged to have our third keynote speaker from National Taipei University of Technology Taiwan, Professor Yu Cheng Fan. To moderate this session, we have Dr. Agung Setiabudi. Please join me in welcoming Dr. Agung to introduce our keynote and facilitate the session.
Good morning, ladies and gentlemen. Welcome to the last part of this keynote session of this conference. Good morning, Professor Yu Cheng Fan. Okay, before we move to the presentation, let me take a moment for introducing our keynote speaker. Professor Yu Cheng Fan is a professor at the Department of Electronic Engineering, National Taipei University of Technology, Taiwan. Where he also served as the head of department, is currently the president of the Taiwan Consumer Electronics Society and actively contributes to the IEEE Consumer Technology Society as treasurer, finance committee chair, and POG member at large. He earned his PhD in electrical engineering from National Taiwan University and was a visiting scholar at the University of Washington, USA. His research interests span AI accelerator design, 3D image or video algorithm and chip design, and consumer electronic system. Over the course of his career, Professor Yu Cheng Fan has published more than 200 journal and conference papers. And he received multiple accolades, including 15 IEEE Best Paper Presentation Award, the Dr. Sherman Young Researcher Award, and IEEE ICCE Taiwan Service Award, and also an STC Industri University Cooperation Outstanding Achievement Award, and several Teaching and Research Excellence Awards. Okay, today in this conference, he will share his expertise with us. The title of his presentation is Emerging Artificial Intelligence and Neuromorphic Chip Technology. This session will consist of 50 minutes, I believe, and including question and answer. Okay, without further ado, Professor Yu Cheng Fan, time is yours.
Today I will introduce our research topic about the emerging artificial intelligence and neuromorphic chip technology. Taiwan is located in the easterly side, Taipei in the North Taiwan, and our school is located at the center Taipei. So this time we come to visit our school and our country. And our school has more than 100 years history, and we were established in the 1912, and there we have the Stephen College, and 10% of the CEO in Taiwan graduate from our school. So our school has a very close, strong link between the industry and the academic. And I briefly introduce myself, and I graduated from the National Taiwan University to get a PhD degree and served to the visiting scholar at the University of Washington, and I'm now the chairman of the Department of Electronic Engineering in our school, and I serve as some service in the IEEE Consumer Technology Society. And today I will divide our talk into 3 parts. The first part is the artificial intelligence and the neural net design, and the next part we will give some example about the bionic design of the new generation AI, and how to perform the AI system it's a real-time processing. So finally, I will introduce the semiconductor technology will drive the high-speed processing of the AI calculation. And the AI intelligence is a well-known idea, and the AI is a simulation of the human intelligence processed by computer. So the AI machine learning and deep learning affect our life very deeply. And the human intelligence includes 2 kinds, 2 levels. The first level is the perceptual level. So when we see, it's just get the signal from the outside, from the environment. However, next step of the human training and the human function is we have the right to learn the anything. So we can think about something and reasoning and tool recognition. So it's the second layer of the human intelligence. So as we see the computer, they must overcome the trouble to achieve the ability of the human being. So many people propose many different ideas of the artificial intelligence. So human has a book as a 7 kind of field, for example, recognition, reasoning, and the association, and the robustness. However, the computer are good at the computation and so on. So there are the different models between the AI and the human being. They are the many new ideas from, for example, early the people proposed the brain propagation, and recently people proposed the AlexNet and the Transformer and the large language model. They want to step for the student and the human being to provide the high recognition rate and propose a new lifestyle. And the AI benchmark debate has gone through real-time history from the Turing machine and the Dartmouth conference, and the scholars proposed reception, and until now they have a new model. For example, AlexNet, ResNet, and the Transformer, and so on. So, however, when the hardware cannot provide enough computing power, they will meet the AI winter. So they are the first AI winter and the second AI winter in the history. And the most important thing is in 2006, the Professor Fekeli to develop the ImageNet. ImageNet is a very huge database provided for training AI model. So after ImageNet has been developed, and the Professor Fekeli holds one competition which is an ImageNet large-scale visual recognition challenge. So according to these 2 big data, and in 2012, the Professor Hinton proposed a new architecture of the AlexNet and use the big data to achieve the high recognition rate. So the big data gives the new opportunity for the AI training and AI learning. And So the 2012, the important year, they push the AI achieve the new generation. And Google also proposed Google AlphaGo to be the top player. And the 2017, the Transformer is developed. And recently, the GPT overcome the many problems. The most important thing of the 2024, the Pofield and the Intel were award the 2024 Nobel Prize in Physics. And another John and Davis was award the Nobel Prize in Chemistry. So the AI not only affects the computer science, but also affects many fields in the science. So it's a trend of the AI research. We discover is increased every year. In the 1997, IBM did Blue beat the World Chess Champion. And in 2002, AI event the home and Rampa also appear in every game. Internet provides a huge data, and the many important AI model use Internet to train their network and achieve the high retention rate. And 2011, the IBM Watson beat the Gemini. And 2017, AlphaGo with the top Go player. So the traditional artificial intelligence, however, the AlexNet or ResNet, the transformer and large language model, they have the big problem because there was a lack of power, and even they have a high recognition rate. However, you need a lot of much power. For example, last year the CEO of Oracle, they say Oracle want to build the 3 nuclear power plant. So the AI server wastes a lot of power. Is any solution to solve this problem? So many companies and many scholars propose a new idea about if we use neuromorphic computing, maybe we can overcome this problem, because neuromorphic computing, they follow the human idea, and they just use the electronic pulse to trigger the signal, and they can save a lot of power, also can achieve the high recognition rate. So maybe the neuromorphic computing is more close to the human being and provide low power consumption. And so for human being, we just need 10 watts to do the calculation in our brain. So if we can model our brain, we can save more power and achieve the same experimental result. So there are many different kinds of neuromorphic systems. The SpineMaker they simulate up the 1 million neurons, and they have the flexibility of the neural operation. However, they have based on the high performance computing approach, is difficult to scale up further. And another chip-based neuromorphic design, like the true nose, Inovatif, and Melalui, can be explained to overcome the related problem. So, however, it's easy to see the Melalui is the most complicated to design as use 2 billion transistors for the neurons. So there are many different kinds of neuromorphic systems. For example, Stanford proposed a neural brain, and the Heidelberg University proposed a brain scale S, and Netflix for the SpineMaker, and IBM proposed the true nose. Intel addressed the long high. So each had a different problem. So until now, the real neuromorphic computing come true. So, but they have the good characteristics for recognition and for power consumption. So maybe it's a new opportunity. So we give the example, if we model the human being, we maybe have the new result for the simulation and for the new AI model. I give another example about the human being artificial intelligence. So we call this model a slow phase network. So when we do the video action recognition, we will look some picture and look the object, and we can just go through this action according to their action to recognize what the people do and what the object do. So according to the human eye model, they have two models of human eye. The first is the slow model. For example, when human eye looks at one picture, we will pay attention to look at the picture very detailedly. At this moment, the spatial resolution is very high. However, the temporal resolution is very low. So when we pay attention to look at one picture to address what the image will show, and we provide a high resolution for the spatial domain, and we can use this to reach the high recognition of the object. And when we just do the glance of some action and very quickly to look at some object to another dimension, the face turn very important to our human eye. However, when the object moving very quickly, the spatial resolution is very low. However, the temporal resolution is very high. So if we combine the two models, follow the slow model and the fast model, we can capture the picture very detailedly according to the slow model, and to emphasize the quick motion according to the fast model. So the idea of the human being model of the artificial intelligence. So this slow pathway and the fast pathway. And if we design a integrated circuit to model these two pathways, we can achieve the target we say. So we design a neural network model layer by layer in service net, the stable superposition layer, and also provide some training data set. And we can achieve and then we use the integrated circuit to achieve the slow model and the fast model with our hardware architecture. In order to reduce the multiplication of the circuit, we use the linear combination process unit because they just few multiplication, but high area, they can reduce the processing area of the integrated circuit. So we use the 3D separator. We can process one dimension for multiple domain and two dimension for spatial domain. So using this model, we can calculate the slow model and the fast model at the same time. So in the detail of the pipeline feature of the efficiency 3D unitary circuit. So finally, we use the digital chips design flow to achieve the circuit that include the algorithm design, architecture design, hardware description language, logic synthesis, for testing, auto placement routing. Finally, we take all the chip to the TSMC, and the TSMC helps us to perform this chip. And this chip uses 40 nanometer, and they can achieve the 700 megahertz to perform the total operation of the fast model and the slow model together. So it's another idea to model the human being to perform the new AI model. However, if we want to calculate more quickly to drive the AI more advancement, so the semiconductor technology plays an important role. So according to the history, we discovered when the 1998, the copper technology was proposed by IBM. So the LSTM and this group can calculate real time according to the copper technology. And when we move to the 2008, the high-K and the metal gate was developed. The immersion laser technology was developed. So it's a laser management engineer was proposed to calculate provide the the big data from the simulation. And the thin-film transistor technology makes the edit state be performed. And the 3D state DRAM makes the AlphaGo to reach the first player. And for example, the chiplet and the EUV technology push the development of the GPT-3. So each new technology push the new AI model. For the semiconductor technology plays the important role of the AI development. So I consider next step, they are the 5 important technology for the semiconductor technology. They include the silicon photonic, chiplet, baseline power delivery, and high bandwidth memory in the customized AI chip. They important 5 trends in the future. So traditionally, we use the copper, we use the cable to do the electronics connection. However, it's very slow and with a lot of power. So they discovered when we connect the die to die on a single chip, we use fiber and they use optical technology. We just need to modulate the signal and can reach a very high bandwidth and high transmission speed. So this structure also can reduce a lot of power of the calculation. So I-to-K connection you need to change by the photonic. But just advanced technology just need to the silicon photonic, for example, under the 3 nanometer. If we use the 7 nanometer and use the silicon photonic, it's no use for the calculation because the speed of the 7 nanometer is not so quickly, and so the silicon photonic just for the advanced manufacturing technology. And the architecture interposer can start to speed up the AI in 2025 this year. And they are several chiplet on a single chip. And the chiplet, connect the chiplet and the chiplet, we can use the silicon photonic like the inside fiber on the chip. So the new recently the many semiconductor company embrace the effort to perform this idea. So consider yesterday and today we use electrical interconnect to connect the die to die or the chip to chip each other. However, this is a high power consumption, and we also need the I/O bump of the chip. If we change another style, we use fiber optical computation. We will establish the very different kind of the optical semiconductor and build the silicon photonic, and then we can connect the photonic, the chip and the chip together, use the optical interconnect. So we can build the photonic compute unit cell and build up the systemic array. And the input signal is mine, and the output signal is mine, because we just need a few bits for the light transmission and can overcome the I/O bump problem. And we also can use the light modulation technology to increase the bandwidth of the data transmission. And we still have a very low visual and the transmission. So if we use photonics, we can improve the latency about 1,000 times. And we use the photonic, we can increase the bandwidth of about 10 times. And if we use photonic, we can reduce the power about 1,000 times. So it's a very important technology when we go near the advanced technology of the semiconductor. So the high performance customer ASIC chiplet, the many single chip connect each other, not only the silicon-based chip, but also the mains chip, the fire chip, chemistry heat chip, and the mains chip. They have a different material of the chip, and it belongs to the heterogeneous integration of the based on the different material. And however, even they based on the different material, they can connect with the same medium, which means the optical transmission. So the optical transmission can perform the connection between the heterogeneous chip on a single chip. So it's a cross-section of the silicon photonic. For example, if we have the high bandwidth memory, ASIC 0, ASIC 1, and another high bandwidth memory, and we use a fiber array to pass through the raw and like the high-speed rail using the photonic. And the low-speed rail, we use an electrical connection in local area. So combine the electrical interconnect and the high-speed rail optical connect, we can speed up the total speed of the whole chip. Another model is the reconfigurable technology. For example, we can consider a single chip as a network. For example, until now, the one chip may include the 17 chiplet or 100 chip. The relationship between the chip and the chip by the network. So it's a network on a chip. So we can build up the network on a chip using the fiber technology. So we use a traditional network architecture can perform the network on a chip, use the traditional model. However, the connection between the chiplet and chiplet using the fiber. So we can use the traditional network architecture to perform the reconfigurable the heterogeneous chip and the system on packaging. So another important thing is the chiplet technology. So chiplet technology will integrate many different kind of material chip on a single chip, and traditional they just use a single chip based on using the silicon material. However, new chiplet they have many different kinds of material. And the AMD proposed many chip include the chiplet in the one package. For example, it's an AMD chip. There are several kinds of the chip integrated on a single package that include the memory, flash, and some G sensor and silicon-based circuit. And there are the many advantages of the chiplet. Like for example, if we use the chiplet integration, we have every company just address the single chip. It's okay. They just need to every company just focus their on their line, and we integrate many different styles from different companies together. Each style is called the chiplet. And they have many advantages. For example, if we use a chiplet technology, then near the DRAM and the die-to-die interface reliability will become high, and the die-to-die protocol layer can be addressed in the format differentiation can be designed by the different company and the article interconnect to connect each other using the network architecture. And this heterogeneous technology includes the MEMS technology, the silicon technology, the biotechnology. Many different kinds of material can integrate with the same chip. And in fact, many products have used the chiplet now. So the first generation, the processor of the AMD and the Intel just use the system on the chip. However, this day, the third generation, we use chiefly the hybrid bonding technology to integrate the different solution on a single chip. So it belongs to the package technology. Not belong to the real semiconductor technology, it belongs to the package technology. So the one example of the chiplet package using ability of the 2.5 dimension and 3 dimension band assembled together, we use a high bandwidth memory and then use the interposer to carry the different memory and the processing. And then finally, we use a package substrate to carry a total signal. And the 3.5 dimension use the CoWoS technology. It means the chip and the wafer and the substrate. So it's in the CoWoS. And until now, we have the 3D technology. So system on the integration dimension chip. So it means the SOID. So there are many different kind of AMD chip also integrate the many different kind of the chipset. For example, Ryzen 9 7900. This chip also use the hybrid bonding of the CCD chip. It belongs to the architecture chip. And another 9004 series, they use the data center for the CPU and the CPU chip, the GPU. Integrate the GPU and the CPU at the same time. So when you stay in the 3D chip on the different dimension, we will increase the capacitance and increase more function on the single chip. So that not only logic chip, but also the DRAM chip or flash chip also use the same structure to develop the 3D integration and 3D packaging. So the millions of the chip package will increase very quickly. For example, mobile data center switch use the 17 chiplet, and the Amazon data center use the 7 active chiplet. It's one kind of 3D system on the chip for the functional partitioning. Every company address their own product, and we integrate the different product together on a single chip. For example, the top is the memory cache, and the second, the wafer-to-wafer bonding, is belong to the packaging technology. Then another company design a microprocessing technology, and they use through silicon via to connect each other on the vertical direction, and so on. We use die-to-wafer bonding, CMOS technology, and they have many different kind of material to integrate on a single chip and integrate the different company product to build a new product. So it's also an AMD chip. When we use stating benefit as the system labor, we can increase 200 times of the interconnect density and propose a high performance of the chip. And the third trend is baseline power delivery. Traditionally, all the signal and the power line just on the front of the substrate. So back of the substrate is nothing. So, but it is a waste of the manufacturer. So, until now, when we go through, when we choose the 2 nanometer technology or 1 nanometer technology, we use the front side and the back side of the whole substrate. And we signal, the traditional signal just use the metal on the silicon wafer, and when we design the power system, we use the backside of the system of the substrate. So the backside, there are many advantages to use the backside power delivery network. They can reduce the on-chip ion drop by the order of magnitude, and they also can scale the chip area, and they can reduce the complexity of the total system, and to reduce the distance between the front side and the back side. So, if we use baseline power network, we can provide the high performance and the low cost of the chip manufacture. If we use a traditional power system, we have the high cost, higher voltage drop, and high RC delay. So the full part of the new semiconductor technology is high bandwidth memory. So high bandwidth memory starts in many different layers on a single chip. So they provide the high bandwidth. Until now, the Hayes for the very high speed memory for the AI application. For example, we discovered from the DDR4 to GDDR6 to high bandwidth memory 2E, we discovered they have over the 358 times to overcome the transitional chip. And also have the high power efficiency to reduce more power. And we use the 3D memory design. So it's a high bandwidth memory ecosystem. There are several families company address pure design, and the memory manufacturer like Samsung, Hayes, and Micron address the high bandwidth memory design, and the other logic design belong to the traditional logic semiconductor company, for example, TSMC, UMC, and Samsung. And they need a lot of company to integrate together to perform the high bandwidth memory ecosystems. And finally is the AI chip. The AI chip is a new strategy in the future. Every different company design their own AI chip. For example, Google design his own AI chip, and Apple design his own AI chip. So many different companies design their own chip. So they have many important tool and the important idea to design their own custom silicon chip of the AI. For example, matrix multiplication of the accumulator, and they also use photonic to connect each other to reach the 1,600 gigabit per second processing, and also use the die-to-die interconnect to achieve the 10 terabits processing, and to access the high bandwidth memory from the memory component called the headers, and also use each package use 2.5 dimension or 3-dimension package system and package technology, and then push their product to the market. And there's a different kind of traditional media GPU and tomorrow's GPU, and we discover when we use a new style architecture to design AI chip, includes artificial input and output, and also integrate the chip together. We have the NVIDIA can achieve the 80 terabit per second processing. So it's a technology platform for high performance computing and the AI. They also integrate the high performance memory and the different kind of the chip from the different company, and use the 3D stacking or system GPT chip technology to package together. And at the same time, we use the silicon photonic to connect each other and to integrate voltage regulation together in a single chip. So when the different companies design their own AI chip, they are forcing to consider they must balance the computer, memory, storage, and network together. The network means on-chip memory interconnection. So they must balance the full important component together. It gives the example for the NVIDIA. For NVIDIA from the 2022 until to move to the 2025, this year, 2026, there are many different strategies. So maybe you want to design the data center and the AI computing center. So they need 5 kinds of chip to integrate together. For example, the graphic processing unit, computing, the CPU, and the NVDIMM, and the network in the chip, and the switch chip together. So when the NVIDIA builds the AI data center, they must integrate many different kinds of chip and at least include the network chip in the total systems. So in the future, there are debates about future artificial intelligence. There are many things need to improve. The first thing maybe improve the computing power. Computing power is based on the structure of the transistor. So then, before we use the FinFET transistor, move to the GA transistor. Next step, we will move to the CFET, and then it has a high processing rate and a small area to perform the LLM model. And the energy efficiency and the green AI is very important. So the Oracle want to, not only Oracle, but also many companies that Google and Apple want to build set up the nuclear power plant. So we predict AI market will use a lot of power. If we can reduce the power, we will have another situation in the future. So there are many different kinds of AI model. For example, if you use the next generation AI model like the Inovatif, and maybe we can achieve the provide the energy efficiency with AI, and the emergence, the spatial hardware, for example, neuromorphic chip design and heterogeneous integration. And another is using the photonic chip or quantum semiconductor, the good solution for the future AI processing. So it's my talk. Thank you so much.
For the most of attendance, the prayer room is available in the same level of this room also. We will reconvene at 1 p.m. for our parallel session. For the schedule and the location of the parallel session are displayed on screen. And ladies and gentlemen, please note that we will kindly ask you for closing ceremony and gala dinner tonight, which will be held in the same room in here at 7 p.m. So enjoy your lunch break and see you. We look forward to seeing you again in the parallel session. Thank you.